Okay, thank you very much for the lovely meeting, to the organizers, and for inviting me. I was not here. I remember last time it was for Zoe's meeting in 2015, so I missed the other Lumini meetings in between. So it's a pleasure to be here. I would like to say this is a meeting on the models of valued fields, so I will start with valued fields, but it's not true. It's at the end. So we will first do something else, and at the end, valued fields will be used. It's rather an application of the model theory of valued fields to difference algebraic geometry questions, and I will use more or less what Yuval talked about. I mean, the automorphism case. So I'm very happy that the talks of Will and Yuval were switched, because it means that the objects were already introduced. I can go even faster, yes. So please interrupt me, stop me if I'm too fast. Okay. Good. So let me start with the Lang-Weil estimates, just to see where the motivation comes from. So fact. So in this form, I state a strong form of Lang-Weil. So in this form, due to Caffrey-Matera, (2006). So Lang-Weil estimates, we all know, for all integers d and l, there exists a constant C, say CD of L, depending polynomially on L, such that if V is an absolutely irreducible algebraic variety defined over FQ, filled with Q elements, of dimension D and of degree L, then we have the following count. So the number of points is of FQ rational points in V is, well, the expected number is Q to the D, which is, for example, realized if you have an affine variety of dimension D, a linear affine, so plane of the hyperplane of the right dimension, and the error term is just of exponent is a D minus 1/2. Okay, so that's Lang-Weil estimates. Let me just say here, the only thing I need for the degree is if V is the vanishing set of the polynomial, say V f1 up to fn, then the degree is bounded by the product of the polynomials. I don't need to know more about degree in this talk. No, it's affine. So you can choose a projective embedding to define degree, or I mean various ways.
The difference with the original Lang-Weil is
Yes, so you have a good dependency on the degree, exactly. We will need that it only depends polynomially on the degree. Right, so we will do Frobenius specializations, and so the degree will be, it will grow a lot, and we need a certain control on the degree. Okay, you will see. Good. Okay, so now, right. So we are interested in difference. In difference algebraic varieties, So objects that were more or less introduced in Yuval's talk, so zero sets of polynomials, where the polynomials now have variables for x, sigma of x, sigma squared of x, and so on in several variables over different fields. Okay. So what is the language? Let's work in the language, say, L sigma, which will be the language of rings, together with a symbol for automorphism. And so polynomial equations with now the polynomials live in this, which is denoted by k of x sigma, which is just k, and then you have variables x, but then you have also sigma of x and so on, sigma squared, ordinary polynomials in these x variables and the iterates. And so in this talk, k sigma will always be an inversive. So it's the contrary of Yuval's choice. Difference field. So in other words, sigma is a field automorphism. Okay? Good. The notation, now the finite, well, if you think for some seconds, you can classify the finite difference fields because you know what the finite fields are and you know what the automorphisms on finite fields are. So let's choose some notation for these. Notation. Okay, so let P be a prime and let n bigger than m bigger than or equal to 0 be natural numbers. Set difference field P and m will just be the difference field given by f p to the n Frobenius p to the m. I should maybe say Frobenius p to the m. So iterated m times. Right? So of course, this is a perfect inversive. Let me abbreviate difference field by df. Yeah, perfect is clear. Finite fields are perfect. The inversive is also clear. And so these are all the isomorphism types of finite difference fields. So sometimes there are two finite numbers. There is the cardinality of the field, and there is somehow the say the cardinality of the fixed field in the algebraic closure of the Frobenius in question. So let me give notations for these. Q will be p to the m, so like the length of the Frobenius, and q prime will be p to the n, the bigger one. Okay? Just for notation. Good. Now let's enumerate them in some way. So here an enumeration of all finite difference fields. Okay. Now we are interested in point counting for different varieties in these finite fields and with respect to a certain limit behavior. So we are interested in the number of points. Well, of course, if you have a difference algebraic variety, you can evaluate it and you can take the points in a difference field. So we're interested in the number of points. Say V is a difference algebraic variety in for this finite difference field. And when, but other than the asymptotics, so for the difference variety, but rather in the asymptotics, when two things happen, so we want two regimes. We want that the Frobenius should not be standard, so it should grow, but the size of the field should grow much faster. So what does it mean? When m tends to infinity, but mi say, but mi divided by ni tends to 0. Okay. So that is, so everything is non-standard. The index of the fixed field is also non-standard in the field, and so on.
But P is fixed.
No, P is also varying. Oh, no, Pi, look, the I has also an index. Here, Pi. So there is, it's all finite difference fields, what I said. Other questions?
MI is a factor of Ni.
No, not necessarily. Well, for most of the time, yes. Let's assume it now, yeah. But yeah, for some things I don't need it here, it's better to assume it, yeah. Okay. Good. Right. Okay. So now let's go to the non-standard world. So I said, the coarse dimension is pseudo-finite difference fields. First, what are our pseudo-finite difference fields? Well, looking at what we want to study, let U be a non-principal ultrafilter on N, such that precisely what I said happens. So according to U, Mi tends to infinity, and this one is equal to 0. Okay? Good. So that's that. And now the pseudo-finite difference field we want to study, or say with the help of which we want to study the asymptotics. No? No? Could be characteristic P. So the PIs, I could concentrate on 1 prime, then we are in the positive characteristic case. So K sigma is not assumed to be characteristic 0. But life is harder in positive characteristic. As we will see, I mean, at least the tools from valued difference fields are harder there, and also other things. So let's look at okay, NIMI, as I said. So just a non-standard version of this, but with respect to an ultrafilter that does the right thing. Okay, so for today, such a thing, such a difference field, so for such a choice of ultrafilter will be called a pseudo-finite difference field. So pseudo-finite difference field. Okay. Now let's introduce what the coarse dimension is in general in an ultra product of finite structures. So, right, the definition: if MIs of finite structures I take some ultra product, I assume it's infinite. Assumed infinite. Then for internal subsets of M to the N, i.e. it comes from an ultra product of sets at the finitary level, okay, we define the coarse dimension, or how do you say, normalized coarse dimension as follows. So, for example, definable sets are internal sets here. Define the normalized coarse dimension of D as, so delta of D. What do we do? Well, we just take the limit in the ultrafilter sense of the log of the cardinality of Di, which is finite, divided by the log of the cardinality of Mi, which is also finite. So this is what? It could be minus infinity if it's empty, and else it will be a real number between 0 and n, because n is the ambient is the Cartesian power I'm working in. Yeah. Okay. Good. Questions? All fine? Okay. So now, so I have already a notion of coarse dimension, for example, in K sigma, because K sigma is a special case. It's infinite by my assumption, and it is an ultra product of finite difference fields. Okay. Now, well, just observe maybe for this one, it has very nice properties. For example, the coarse dimension of the union is a maximum of yes. So and Cartesian products etc. So it has some nice properties, of course, when you have a subset, and I mean, it behaves very much like a dimension function. Now, a second notion of dimension, which we only have in difference fields. So let L sigma be any difference field. Any means still inversive, but it doesn't matter here. Difference field. Pi of x, a partial n-type, over L. So it's a collection of formulas in n variables with parameters from L. Then we set the transformal dimension. Well, let me say with respect to the theory of L of pi, it will just be you take a solution of pi of we take a maximum of the transformal transcendence degree of a solution in an elementary extension. So the maximum of the transformal transcendence degree of the field L of A bar sigma over L, where A is in some L prime, elementary extension of L, and A is a solution of my partial type. So the usual notion, yeah, you want to define dimension, you can, for example, look at solutions and take a maximal one like this. Okay, good. And now I also want to define, so if K sigma is as above, is a pseudo-finite difference field, we set, and pi of x is over K, set delta of pi. Up to now I only defined delta for definable sets and not for partial types. So we'll take the infimum of delta of phi of K, where phi is in pi. Yes?
So if sigma is the identity on L, and pi of x is x equals x, then what would be the dimension? Would be 0 or 1?
What are the if sigma is the identity?
Because what if it's an elementary extension of L, right? It's not an intrinsic thing.
No, it's
just one dimension in ACF.
I work in an elementary extension of L. It should be of L sigma. Yeah? I mean, yeah. So of course it's intrinsic to the model.
Yeah.
For example, if it were a pseudo-finite difference field, if there is no point, there is no point. I don't want to assign to it. I don't want to go outside. I don't want to take the ACFA. I don't want to take the ACFA dimension here. Of course, it's related, but no. This is totally general. You can always do this. Any difference field, any field, you can do it. Model this. That's why I wrote carefully down the thing, because it's yeah. And now, of course, if we have this, so look, so we can take the infimum over the coarse dimension of the formulas in it. Okay, questions so far? Okay, then I can state the first theorem. Let me put it maybe here. Oh, okay. So theorem A. Not yet fully written up, but almost. So, if pi is a quantifier-free partial type, over the pseudo-finite difference field K sigma, then the two notions coincide. Transformal dimension of pi is equal to cos dimension of pi. Okay, that's the first result. So good. So let me say, let me give it a moreover. In particular, delta of pi is an integer and not just an arbitrary real between 0 and n. And moreover, and if pi is over some countable set of parameters, then I can compute its dimension because K sigma is Aleph 1 saturated as an ultra product, then delta of pi is nothing but the maximum of transcendence degree, transformal transcendence degree of A over A, where A is in pi of K, solution of the partial type. Right? So this is just because I find if there is someone in an elementary extension, I can already find it, someone like this in K itself. Okay. Good. Questions? No? Yeah, but I can close it under sigma. It doesn't change. Yeah. Yeah. Okay. Field generated. Okay. Yeah. Okay. But you can always take the sigma field generated by, and yeah. Since it's a pre-geometry, it doesn't. Yes. Yes. Okay.
So the field that you define is always smaller than the transform dimension in the sense of ACFA. Is it the same as ACFA as well?
No. I mean, it can also be. Okay. It depends on it can even depend on the completion of ACFA. For example, you can have things which over the field itself. Okay. If you're through the wrong completion, for example, if you embed it not in a relative algebraically closed manner, for example, you can even go down. Okay, I don't want to get into it.
Which is transforming transcendental, totally transforming transcendental.
So it can, okay. Yeah, so you see what I mean? You can, for example, you can write square root of 2 is switched by sigma, but you don't have square root of 2 yet. And then you do something, but then it depends on the embedding. It can depend on the completion. I don't want to get into it. It's a delicate issue in some sense, but let's not discuss it. So, not yet. Later, yes, but I cannot assume they're absolutely reducible because I'm not over an algebraically closed one. So it's indeed an issue. Yeah. Yes. So later. Yeah. Okay. Let me give a remark on. So, of course, there is a famous paper by Zoe, Blau, and Angus. Let me put this in the remarks. So it follows. It's a very special case. They have a much better count. So, but so if you are in a pseudo-finite field, in F, let me say, pseudo-finite, pi any partial type over F, then the cos dimension of pi is equal to, let me say, a formula. We can deduce the other result. A ring formula over F. Then the cos dimension of phi is given by the algebraic dimension of the Zariski closure of the solution set. So in that sense, it's the algebraic dimension and not the transformally algebraic dimension. So it's the same thing as the maximal transcendence degree of a solution in an elementary extension. So completely simple. But of course, they know more, yeah? So here you know that it's by the Lang-Weil estimates, which are where is it here? The key is to this result is the Lang-Weil estimates. But one even knows, if you look at it here, you even know the coefficient in front of q to the d. We only detect the exponent in our theorem. The exponent is d, and the exponent is the only thing which is detected in theorem A, not the coefficient in front of q to the d, but the exponent. Right. Okay.
But do you get, in the case of the quantifier formula, do you get that the coefficient is integer? Or not?
We don't know.
You don't know.
We don't know anything. I don't know. Maybe we could know, but we don't trace it. No, one could know maybe, but so if you want the main part, yeah, no, one can certainly say, one could maybe say something. We can bound it in terms of the degree of the variety. Yeah, that's obvious. Yeah, but of course the lower, yeah, we also get at least one in the coefficient. If that, yeah, we get at least one. If it's not just 25, yeah, at least one. At least one. Okay. We cannot do two things at the same time, right? That's a bit. Okay. So I will now introduce some notation. There's no eraser? Yeah. Ah, there is one. Yeah. So maybe I can already tell a story. I mean, how do we prove theorem A? Of course, we want to use Lang-Weil. And so we have to get enough control to, I mean, difference varieties over a finite difference field, they are also varieties over a finite field because you plug in Frobenius. So the whole point is to control this procedure of plugging in Frobenius. That's the main thing to be done. Okay. Right. So part 3. So some difference algebraic geometry, Frobenius specializations. Okay. Let me introduce some notation. If L sigma is a difference field, X in AN, a difference variety over L, so one knows that any such is given by finitely many equations. There is a Noetherian topology on the zero sets of difference polynomials. So I have finitely many polynomials where the pi come from Lx sigma. Okay, so this is called a difference algebraic variety over L. So if X is irreducible, so since the topology is Noetherian, every difference variety is a finite union of irreducible components over L. So if X is irreducible, set transformal dimension of X is a transformal transcendence degree of, well, so say the function field of X over L, what does it mean? So where I of X is the prime difference ideal defining X, right? And L of X sigma is just, you take the field of fractions of note that this is not yet inversive. Let me maybe take sigma, sigma inverse to make it inversive. Yeah. Well, here it doesn't matter because the transform and transcendence degree is the same. Okay. Function field, and if it's a finite union of the irreducible components, you just say the dimension is the maximum of the dimensions of the components. Yeah. Okay. Yes, you're right. Okay. So, yes, I know. Okay. Now it's true. Okay. Okay. Want inversive closure? Okay. Good. Now let's look at the finitely generated difference subring. Actually, it's better. It's a difference domain. What does it mean? It's an integral domain, so that sigma is an endomorphism. It's automatically the case because it lies in a difference field, difference domain. Yes. So a finite, an injective endomorphism, thanks. So such that the PIs, they all lie in D of x sigma. Okay, so the polynomials are already over D. Okay, now look at eta. Eta is a specialization, so it goes from D sigma to some difference domain. B sigma, so now I should say it correctly, B is an integral domain and sigma is an injective endomorphism on it. So I specialize to it, so this also lies in a difference field, B sigma. Okay. And then x eta is defined by P1 eta, M eta is 0. So just you take the coefficients, apply eta to them, you get a different, so it's like base change to via eta to B. Okay. Good. And now I claim there exists D subset in D of D prime in the fraction field of D prime finitely generated difference domain such that for all eta from D prime to B specializations, the transformal dimension of x eta is bounded by the transformal dimension of x. You basically have to invert all the coefficients you need to witness transformal algebraicity. And that you do, finitely many. Okay. Good. Finitely generated still. Okay.
Is eta injective or anything?
No, eta is not injective. It's just a map of difference rings. Could be, for example, Z with identity goes to FP with identity. Okay. Not very interesting, but yeah. Okay. Questions? So, okay, where are we? Now comes the important part, namely we want to go to the finite situation. So LQ notation is FQ alg together with the Q Frobenius. So if for Y a difference variety over LQ, set MQ of Y, the algebraic variety you obtain replacing the use of sigma by plugging in what it does. So the Frobenius specialization. Of y, okay, obtained. Okay. The algebraic variety obtained replacing sigma of x, sigma to the m of x by x to the q to the m in the equations. Defining y. Of course, same solution set. We didn't do anything in LQ. This means that it's, of course, another object when you go to extensions, but in LQ it's the same object. Okay, main problem for what is to come. So we want to count looking at this algebraic variety. So the main problem is the following. Main problem, control locally the algebraic dimension say of MQ of some specialization of X you got when eta was with was a specialization map going to some LQ. Okay, so theorem B, which addresses this, and then I will talk about proofs. So first, okay, so let X in AN be a difference variety of transformal dimension D over the finitely generated difference domain D sigma. So what I mean is it's of this dimension in the fraction field of D. Okay, if you have this, then there is a different subvariety, XS, somehow special, of X defined over D. So polynomials use only coefficients from D, of transformal dimension less than D, strictly, transformal dimension strictly less than D, and D prime in the fraction field of D prime finitely generated difference domain, such that all Frobenius specializations starting in D prime, not in D, starting in D prime, so such that two things hold. If I go from D prime, so if I invert it in enough people, well, first of all, I need to choose Q large enough, and enter any specialization to my difference field LQ. And the algebraic dimension of the specialization of the special subvariety is less than D. That I can already do by what I said before. Just choose D prime so that you invert it enough. And this is important. This is easy, but now comes the important thing. X eta without, well, MQ of X eta without XS eta. So if I take away XS eta, this is X minus XS eta if you want, is pure dimensional, is of pure algebraic dimension D or empty. Could also be empty. But if it's not empty, it's of pure dimension D. Right? So that was your question.
So this is the same as ACFA, right? So here you mean transformal dimension.
Yeah. But, okay. Good.
Do you know any bound on the number of components?
No. Well, apart from the degree, which is a trivial bound, but okay. 2, Now the count. So assume, so you have a non-empty open different open different subvariety with U defined over F over D as well. So just to take away, you take away some proper closed subset defined over D. Then there are constants, little c, capital C, constants bigger than 0, depending on x and u, such that for all q, say it's p to the m, bigger than c, and for all eta from d prime going to LQ, for all t positive natural number, if eta of d prime happens to land inside fp to the t, so the coefficients are all in fp to the t, and there is a point x, a rational point in this Frobenius specialization of u without xs eta, so not lying in the special subvariety but on my u, okay, in over this finite field fp to the t, if there is one, with rank of the Jacobian of this algebraic variety mq of, doesn't matter, I can take u also, eta at x of rank greater or equal than n minus d, where I defined it. So we lie in a to the n, yes. So the complementary, yeah. D is the dimension of the variety, n is the ambient space. Okay. Then we have a count, because this point will be smooth. And it will lie on an irreducible component defined over fpt, not anything. So two things at the same time. This point has to be smooth because we are pure dimensional, so it has to be of the top dimension. It lies only, okay, anyway, we'll see in a second. But so now we have a count. So then we have the count mq of u eta of fpt, is at least p to the dt minus some error factor, q to the little c. Remember, q is much smaller than p to the t. I mean, it's interesting. Q to the little c, p to the d minus 1/2 t. Okay. So that is the second theorem. And that also shows how we want to prove this. Yeah, because somehow the critical thing is finding a smooth point which tells us that I find an irreducible component of top dimension over the finite field, and then appeal to the strong form of Lang-Weil, and the bounds are okay. Because, yeah, what we get is in the medium regime, so it's not really. I mean, it will disappear in the log computation. Questions? Here. They depend, okay, on the complexity of x and u. Yeah. So this is true because xs. So the definition of xs the complexity of xs is bounded in terms of the complexity of x. That's the crucial thing, right? Yeah. Yeah. Okay, that is a different story, right? But xs, I see. Yeah, that should also work. Okay. Note I should say by 1. Okay. Note by 1, the dimension of MQ x eta is at most D. And so the upper bound is trivial. So, well, trivial, easy. So Q to some C, which is basically the number of irreducible components, which you can get in, it's a function of the degree, yeah? Times P to the dt. And so that's fine. So the critical thing is, of course, finding many points, which is this one. Okay. Good. Okay, 2 minutes left. Okay, proof of 2. So the point x in question is smooth. But because by equidimensionality it doesn't have any other chance. The Jacobian rank is what it should be. Okay. So it lies on the unique, and it lies on a unique component. So the unique, absolutely irreducible component of MQ of x eta it lies on is over FPT. Because if it were 2, they would all be conjugate around the point, and they would have several, and they would not be smooth. So this is impossible. Yeah? Cannot. So we have 2 things at the same time. We found a component, absolutely irreducible component defined over FPT. We are done by Carfore Matera. Yeah? So 2 follows from strong Lang-Weil. Okay, that's that. And now the proof of 1 needs a whole story, but Yuval has told the story this morning, well, a similar story. So proof of 1, and I'm not sure, I think I cannot give everything. So what is the problem? The problem is this, yeah? Maybe your point x lies here and you don't like this, because then you don't know anything. So this is to be avoided, so that's why I want to make it pure dimensional. So there is a surface, there should not be a curve. I want to get rid of it. So that's a problem. Okay, so 4. So this morning, Yuval's talk, we have seen VFA is a theory of, yes? If this is the Jacobian rank doesn't tell you the point is smooth.
Which point?
I have a point x. There is a little x here, an FPT rational point, which does not lie on this special subvariety. In the second line from below, the little, and that point lies, or it's a smooth point because It lies on some irreducible component.
I mean, the other components, they don't count anymore, right? I mean, if you count the points on them.
Yeah, okay, good. Do you agree it's a smooth point? Okay. X does not appear in 1. No, x does not appear in 1. That is true. But I want to, okay, it's not the problem for 1. It is the problem why I want 1, sorry. I want 1 because I want to take away I want to take away a different subvariety so that the specialization is equidimensional or empty. Okay. Right. Yeah? Did you agree? It's okay? Good. So sorry, so it's not the problem for the proof of one, it's a problem that we face, and so that why do we want one? We want one, yeah, because of this problem. Okay. Good. So VFA is the theory of omega increasing inversive. Let me put it, because I'm only looking at these difference field, value difference fields. Okay. And here's now the theorem by Yuval and Udi. Which saves us the day. So what is the idea? The idea is, I don't know how to talk about this. If I had the strong topology, so evaluation topology around, then I could say around my point, I am of dimension so-and-so. And the good news is the value difference field, the theory of value difference fields we get has equality of transformal dimension and topological dimension, as algebraic value fields have it for algebraic dimension and value. And that is the good news. So we can use the strong topology to detect locally dimension. Okay. So yeah, I should come to an end. Let me just do this. So in characteristic 0, it was done by Salich before. So what do we have? So VFA has a model companion VFA tilde in the notation from this morning. 2 if L, gamma L, little kl, sigma is a model, then the residue field, the residue difference field is ACFA, right? And stable embedded, and purely stable embedded. So it is a pure difference field. 3, if LQ tilde is FQ of T alge, T at evaluation, and Frobenius Q, then VFA tilde is the limit theory. So for Q large enough, you hold if and only if you are in this theory, as Yuval explained this morning already. In particular, non-principal ultra products of LQ tildes are models for non-principal U. Okay. And also what follows from this, also VFA tilde implies that it's also the full field is also ACFA by this theorem here. Okay. And 2 more things, 4 and 5. Let me put 4 here, and then I stop and explain verbally what we do. So if x in L to the n is L sigma definable, right? In the model, in L a model, then the topological dimension or the transformal dimension of x is equal to the topological dimension for the evaluation topology of x. Maybe not everybody knows topological dimension, just you take the largest number of coordinates where you can project and the interior is non-empty. This can easily be proved. So we can use it to detect dimension. Okay, and then finally, 5, PO of x, which just says x is in O, and residue of x is sigma transcendental, is a complete type, is a complete definable type. This is more difficult than it looks. Okay, so one uses this so just to finish verbally, we embed our difference field trivially into a model of VFA. So as a trivially valued subfield. So we have two copies of our object in the full field, because we can identify the parameters upstairs and downstairs, and in the lower one. And then we can somehow say over my point hangs the whole, so rest to the minus one of a d-tuple is the full ball. So we can see what the dimension is. But the good news is that the object lives in the residue field. So whatever we define there using the valuation outside by property 2, pure stable embeddedness, we are allowed to use extra language. We are allowed to use the valuation. And what we did was, at the end of the day, only difference algebraic. And to make it work, 5 is used, yeah, because you somehow play, okay. So with this, you find the XS in question. You just have to, this is a little computation, and then it's also nice, because if there were counterexamples, so going from theorem B to theorem A, if there were counterexamples, we could find larger and larger ones, but then we could somehow embed them into such a situation, because this is the limit, yeah? So we can always embed. So I will not explain the details for that, but to get theorem A from theorem B, there's one final step. Why do we get smooth points? You twist, so you have a sigma, maybe the reduced limit degree, so now for the expert it's not the limit degree, so you get algebraic, but not separably algebraic. You twist your sigma and you replace it by sigma to the times Frobenius to the minus some power, but this is done once and for all, so it doesn't affect the count at the limit. So twisting the automorphism, you can find a situation where the derivative is non-zero, and by the primitive element theorem in difference field, you can think of a hypersurface not by one equation, but by codimension 1. And so you can find many situations where the Jacobian is non-zero, actually. Up to a definable bijection, which is not a problem for a count of points. Okay, thank you.
Thanks for the talk. So, can you conclude from this that the model theoretical algebraic closure over those pseudo-finite difference fields is transformally algebraic?
Oh.
Because if you say that it's the same as in alpha, that's like strongly suggestive of something like that.
I think they can be wild. No, we don't know. I mean, I think, well.
You know they're very wild, right?
Yeah, but I don't know. I don't know. So you said the model theoretic algebraic closure in case sigma.
Yes, is transformally algebraic.
Transformally algebraic.
Yes.
That should hold. That should hold. That certainly holds. Sorry, that certainly holds. I thought that should hold.
What's the example?
But I mean, it might be even
No, transformally algebraic, that should hold.
Yeah, even under weak or something.
Yeah. No, that is, I thought you meant ACL sigma. Okay.
but I think it should be ACL.
That I'm not sure. Okay, I don't know. Okay. Okay, maybe, yeah. Okay. I mean, we don't have a full understanding. I don't know. Yeah. We haven't investigated the theory of. Yeah.
Actually, a second question, and I think it does follow formally. So,
Okay.
if you have a pseudo-finite difference, and then you have an extension which is of S to rank omega n, like it's transformally transcendental.
Yes.
Does it follow that it embeds the neutral power? Like it's
Yeah, of course. There is a solution. Yeah, I think. You mean transformally transcendental.
You have a pseudo-finite difference field of the
Yes.
field that
So
you
K
described.
sigma. You have a K sigma. Yeah.
And you have a transformally transcendental extension.
Yeah.
Then does it embed already the neutral power?
I mean, there are transformally transcendental elements.
No. any extension which does not
any.
contain transformally algebraic elements.
Ah,
This is
so
the
you mean
element
like
of being
transformally regular? You want
transformally regular
yeah, I
extension.
see. I
Is it
see.
transformally PAC?
Yes. I don't know. Good question. Yeah.
Does it not follow from?
Yeah, it's possible. Yeah. Well, but you need to be. The problem is, okay. Yeah, is it enough to have this? Yeah, but you need to know that it's the variety you describe is somehow irreducible. Yeah, even over ACFA. I mean over, right? So, but it's okay. Okay. Yeah, it's possible. I could follow. Yeah.
Do you have
At what point you use that Frobenius power grows much slower than the cyber field?
Yes.
So why do you use it in your proof?
At the point where, for example, here, you see the Q to the C should be small. So that you really need the, yeah, I mean, look, I mean, sigma of x1 is x1 and nothing. x2 is x2. You have q prime many solutions, but you want to forget the q in the exponent. So logarithmically. Of course, then there can be finer questions, but yeah.
Yeah, but if it was bounded, then it would be an algebraic extension.
If okay, if you mean if the fixed field were of finite index, yeah,
Yeah,
then we know everything.
yeah. No,
Yeah.
but my
Right?
question was, do you know anything about the completions?
Well, we don't know anything. Well, actually, I take it back because there's still the automorphism. Okay, yeah.
I'm sorry, what?
If the fixed field is of finite index, you mean, then we know everything, yes? Because
Yes,
then,
we
yes,
know everything.
yes.
No, so, but do you know anything
Yes.
about the completions of your, your...
I mean, as I said, we haven't investigated the first order theory, so I don't know. I don't know. It's very, this is really about, it's really a rather, well, you just understand the quantifier free set, so it's not going beyond, the algebra, so to say.
So do you know anything, for instance, about neostability?
No, I mean, nothing. I know nothing, maybe Udi knows, yeah.
I'm a bit confused now what I know, but there are some these counterexamples in Tetris T, don't they apply? That shows you can interpret,
Oh, yes, yeah. The bilinear forms. Yeah, I guess pairs of pseudo-finite fields, they're messy anyway. Right, you can interpret arithmetic, but I think not all of them, right?
I mean, I should have said this is somehow a long-term project of Ting Zhang, which which she had looked at a long time ago, and Udi gave the way to do it. Yeah?
well, after the conjectural seems very difficult to make.
Okay.
Yeah, it's very.
Can you say something about why 5 is used in over there in the proof?
Phi?
Yeah, 5, condition 5.
5. Ah, yes. So 5 is used. 5 is used because when you take. So as I said, somehow we have two copies of our. We have our K sigma maybe sitting inside the residue field, right? But we can choose a lift, yeah. So it's trivial embedding. It sits also in here. So we choose a lift. I should say that sigma Heinz-Zielin, there is also a lift. So a sigma equivariant lift of the residue field to the field that exists. So I can look at this. I also have a copy of this. So I have a copy of the variety twice. And now if the transformal dimension is D, then I find a D tuple, which is transformally independent, in the trivially valued subfield. And this is, of course, a solution of PO to the D tensor product. And then I know if I take anybody of this type, it does the same. So that's why, if you choose, I mean, that is what is used, yeah? So you know that for such a type, if something in the value language happens, for example, the fiber is non-empty or something like this, then you know it also for any other such tuple. Yeah. So you know it for x, you know it for, okay. You know something for x1 up to xd po to the d, right? Then you can also perturb it by someone from the maximal ideal. Yeah. Then it has the same type as x1 plus epsilon 1, xd plus epsilon d. And so, for example, if this is in the projection of the whole ball will then lie in the set you're looking at. Okay, I don't want to give the proof, but then you can show that the interior is non-empty using the fact that close by you have the same type. Okay. Over the parameters, the difference variety is defined over. Yeah, you've chosen a generic, and then somehow you choose a transformer transcendence basis of the tuple of the generic, and then this is in O to the D. It's a solution of that type, and the fiber is non-empty of my projection map. Then it's also true close by, so that means that the whole open ball has non-empty fiber, but that means that the interior of the projection is non-empty. See what I mean?
Okay, so maybe we'll stop here. So thank you so much.